冯诺依曼带来计算机领域的3定律。1948年，香农在和冯诺依曼的讨论后提出信息熵和香农定理。20世纪初期，菲尔兹在证明黎曼罗赫定理的同时，致力于全球数学交流。1941年，海蒂拉玛和安泰尔发明的调频技术落地于无线通信系统。1965年，戈登摩尔总结实践经验，提出了一直被追赶的摩尔定律。2000年。
Hello, everyone. Welcome to the Charles Park mini course series in Fundamentals of Channel Knowledge Map from Classic to AI-based methods. Here comes to our last lecture, Lecture 4.2, Channel Map for Intelligent 6G Networks, a scatter-based modeling and reconstruction framework, delivered by Professor Ray Zhang from National University of Singapore. Today, we are very pleased to have Professor Ray Zhang, an IEEE Fellow, Provost Chair Professor from National University of Singapore. He's also an adjunct professor with the Chinese University of Hong Kong, Shenzhen in China. Professor Zhang received both the bachelor and master degree from National University of Singapore and also the PhD degree from Stanford University. Professor Zhang has been serving as the chair for IEEE ComSoc WTC Award Committee. He was the distinguished lecturer for both IEEE SPS and IEEE ComSoc. He has served for more than 30 international conferences as TPC co-chair and organizer. He is in the editorial board at MPJ Wireless Technology. He was the former editor for IEEE TWC, TCOM, TSP, JSAT, TGC, and etc. Professor Zhang has achieved great academic achievement and recognition, including he is a fellow of Academy of Engineering Singapore. He has been recognized as highly cited researcher since 2015. He has published more than 600 papers, where 18 of them won the IEEE Best Journal Paper Awards. He has received 2 times for the IEEE Marconi Prize Paper Award and 3 times for the IEEE Heinrich Hertz Prize Paper Award. Without further ado, let's join me welcoming Professor Zhang.
Okay, thanks, Junting, for the kind introduction and also hosting my talk. Just let me share my screen. Okay. Can you see it, Junting?
Yes, we can see your screen.
Okay, so maybe I shall start. Okay, so hello everyone. This is Ray Zhang, and from National University of Singapore. So today I'm very glad to have this opportunity to give this talk on this very promising topic, channel knowledge map. And would like to first thank Charles Park for the invitation, and also I realized that actually I will be the last speaker, right, for this course series. So I think by now, the previous speakers, including Professor Chen and Professor Zheng and Professor Xu, and they have already done, I think, they're very good jobs introducing the channel knowledge lab and also, the construction algorithm and applications. So I think you have already learned a lot, for this very promising area. So I think today maybe I will, just Okay, so this is outline my talk. Okay, so I will still give a very brief introduction about this channel knowledge map, and maybe give some views from my own perspective. Okay, so to hopefully provide you some additional insights for the CKM. And also, I will give a brief overview about existing CKM construction method, although they have already been well covered by the previous speakers. But I will just quickly go through them and maybe give some comments about their advantages, disadvantages. And then I'll introduce a new approach, which is actually recently proposed by my group, which is is a so-called scatterer-based CKM modeling and construction. And I think this is a interesting new approach. It's related to the some of the existing method, but also has its own novelty, and also has some advantages. And later I'm going to show you, I mean, some performance, some capacity advantages compared to the existing CKM construction method. And then I will conclude this talk and point out some direction I think worth investigating in the future. Okay, I think we all know, right? We are now at the area of 5G, and now we're looking into the future 6G. So there have already been a lot of exciting literature and also online talks talking about 6G and various aspects, like the 6 typical usage scenarios. So I don't think I need to repeat that. But here maybe I just want to point out that from a wireless network operation perspective, actually we are seeing a quickly evolving trend for 6G. Actually is we can see more roles of AI and also wireless sensing, primarily due to the ISAC, integrate sensing and communication new function of 6G, and also environment awareness, right? So you can see that the future network operation will be built based on these very three important tools, right? AI, sensing, and the environment awareness techniques. Now, one reason is perhaps that in the future 6G that we have AI run, right? AI-driven radio access network. So that need a massive network level of wireless channel information, right? For the AI agent training, decision, and self-control, right? Such as they can do more intelligent resource allocation and network management for 6G. And also, the ISAC, right, feature that provide, more capability for the base stations to do sensing, in addition to communication, and then also integrated with AI algorithm that make this, environment wire network operation more feasible, right? So we can imagine that in 6G, there will be more and more environment wire network operations as compared to the existing 5G. So maybe you wonder, right? Now look at our existing wireless network, for example, 5G, right? Actually, do we are we not utilizing any environment awareness? Actually, of course. I mean, we are already exploiting, right? CSI, right? The so-called channel state information, which is function of the environment, right? The propagation environment. However, a traditional wireless networks is maybe I think is that it does not explore the CSI in a very sophisticated way, right? For example, we know, right, traditional network the deployment phase, right? I mean, where to put the base stations, right? Usually we will consider the channel statistics, right? For example, right, what the coverage area, what is the, the pass loss coefficients, shadowing loss, in the given area, but not really catering to the exact environment, right? For the area of interest, right? For example, maybe they will consider, right, the base state deployment for urban area, but we know, right, for urban area, we also have a different, right, city, layouts, right? For example, Shanghai will be very different from Shenzhen, right? So you can see that the environment information is not really explicitly, right, considered in the network deployment phase. And also, right, because the base station need to support users, right, that are moving around, right? So their channel random, right, and change over time. So in traditional wireless, communication system, we use pilot-based, right, channel estimation, right, to obtain the real-time channel state information, right, such as we can do efficient beamforming, right, data, demodulation, and so on and so forth. Okay, so but there's a problem, right? The reason is that as now the base station has a more and more antenna, right? We know there's a massive MIMO system, but into the 6G it will be extremely large scale MIMO system, and the channel estimation overhead will become more prohibitive. Okay, while the traditional, pilot-based channel CSI estimation actually does not explore any prior knowledge about the environment, right? So basically, you look at existing, channel estimation scheme, right? They basically assume the channel is, ID, right? Maybe, complex Gaussian random variable, right? So does not really explore any prior known statistical knowledge, right? Depending on the environment where the user is located, right? So from this discussion, right, probably you can see, right, we have, for the past generation wireless network, although we have exploited, the relationship between environment and CSI, either statistically or instantaneously, but not in a very sophisticated way, right? And so this is left a big room for us to improve, right? So we can do better network deployment. We can also do more efficient real-time channel estimation for data communication. So I think this is all of this has motivated the channel knowledge map, right? Which is a very general concept. I think it's a models, the functional relationship, right, from a wireless environment and the spatial transmitter receiver locations to channel knowledge. So here I want to maybe elaborate three main points in the CKM definition. The first is that it depends on the transmitter and the receiver locations, right? So you can think about, right, either the transmitter or receiver location change, right, the channel will change, right? So in general, right, if you think the transmitter location is 3D, right, receiver's location is 3D, right? So actually you need, if you want to have a fully characterized, right, for arbitrary transmitter receiver location, actually you need a 6D, channel map, right? But in general, like you look at our existing, channel knowledge, right? Usually it's a either 2D or or 3D, right? So because we're assuming fixed transmitter, right, base station, while the user are usually on the ground, right? But actually, in general, right, if we really want to have a full, channel knowledge map, actually, what we did is a 6D, right, dimension mapping from the transmitter user location to the channel knowledge. Well, secondly, you can see, right, this depends on the environment, right? So traditionally, we have a statistical channel, information, right? For example, pass loss, okay, shadowing parameters, right? That is already averaged over, many similar environments, right? Like urban environment, for example. But actually what we can see here, right? The CKM provides an environment specific channel, knowledge distribution over space, right? So, in one district in Shanghai will be very different from another one in Shenzhen, right? So this is the second one. It's a highly environment, dependent, okay? Or you can think of site dependent, right? Mapping. Well, the third one is that the channel knowledge, right? Actually, channel knowledge is a very general, concept. All right. Of course, you can think of a channel is a baseband channel, right? It's a complex channel, right? If I have multiple antenna, there will be a vector, right? If I have MIMO, it will be a metric, right? Well, but in practice, right, usually when we use a channel knowledge map, actually we do not really use the exact channel at the exact location, right? Because we know, right, we have an infinite number of locations, right, in a given area, right? So if you want to obtain the channel knowledge, the complex channel for all continuous locations, right, it's not possible, right? Because we have an infinite variables to characterize. So you can see in practice, usually we use lower dimensional, manifold, or some kind of statistical average, in the form of either in the frequency spectral map or in the angular map or channel gain map, right? So you can think of that. All of those are, you can think of additional mapping from the actual channel knowledge to some lower dimensional manifold. Okay, so this is I think from my perspective, this some main points, I think important points I want to highlight for the channel knowledge map. Now, overall, right, you can think about generally, right, although you have a different CKM maps, but they all enable location-aware a priori channel acquisition or information, right, such as that we can reduce or even, obviate the need for real-time channel estimation, right? So the main objective is that to provide a priori channel information, right? That could be helpful, right? For us to achieve design objective, but with a less real-time channel estimation overhead. Okay, so a CKM will be I think is a key enabler, right, for the future environment while 6G network operation. But actually, CKM is not a really completely new concept. Right? Even dated back in 2019, actually, one of my former postdoc in my group, Professor Shuji B, and also some collaborators, and already proposed, the similar concept I call the radio maps, right? And also with its applications for wireless resource management. But I think channel knowledge map is a more general than just the radio maps when that time we envisioned in this article, because it provide I think a systematic way how to make use of the channel knowledge, the spatial and the distribution, and including typically three phases, right? First you have to obtain the CKM, right, offline, right? And this is usually based on the available environment map, right, which will give the topologies, the building distributions in the area, and the plus, right, some channel measurement data. Right, could be labeled, or labeled. What I mean is that with the location tag, or even not labeled exactly. Right. So based on this, right, we need to offline to construct CKM. Right. Well, we know, right, the CKM constructed is based on the static objects, right, scatterers in the environment. But in real life, right, actually the environment is dynamic, right? Some of the object may move around, right? The topology may change over time. So we still need to do frequent real-time CKM update, right? You need to update the CKM over time, right? To keep track of, right, the up-to-date channel distribution. And this also involves, for example, sensing, wireless sensing, to identify any change in the environment, or the real-time channel, the additional channel estimate data, available. Okay, so after you do the real-time, CKM update, right, over time, and then you can now have the knowledge of the channel information of prior channel information, okay, and up to date also, right? And then you can use the such CKM, right? The last phase will be CKM utilization, right? I mean, you can use it for different purposes, right? For example, for communication, it could be network resource allocation or more efficient palette design, right? For real-time CSI estimation. And you can also do a sensing or localization, right? Especially for a non-life science environment, right? I think one of the previous speakers has talked about how the CKM can help to do better or more efficient non-life science environment sensing and localization. Okay. And so we can see, right? We can envision that channel maps, right, in different forms can provide many interesting and promising applications, right? I think some already covered in this course series. And for example, right, localization sensing, the network deployment, right, where you deploy the base stations or the intelligence surfaces, and how you do the resource management, right, like a beam, assignment, like the code book design, and the frequency allocation, and also like robotic, right, in future robotic automated system, right. I mean, all of this you can think about this robotic, like UAVs, right? Like on ground autonomous vehicles, right? And their communication performance, right, will be critically depends on the environment, right? Because they move around, right? So they will have, especially you have D2D communications, right? A peer-to-peer communication among these robotic agents, right? So their channel is more dynamic, right? So in these scenarios, right, prior knowledge, right, for channel maps will I think will facilitate, right, to design their trajectories, to predict their channels, in the future time, so such as to achieve more reliable, higher throughput communication links among these robotic agents, right, like UAVs. Actually, this idea has also been explored based on my knowledge, right, even early in 2021, even before the channel knowledge map, the concept was proposed, and actually, Professor Yung Zheng at that time is a postdoc in my group. Actually, we come out with this very interesting, I think this interesting concept using the UAVs, right, in the flying in the cellular network, and it can do simultaneous, navigation. I mean, they have their own, mission, but at the same time, trying to do the channel management to construct a radio map, right? And also integrated with some deep reinforced learning, some AI methods, right? So it can, I think this is an interesting paper. Actually covers some of the interesting ideas that involved in the radio map construction and also application in communication, wireless communication systems. Okay, so I think I have just done, introduction, right? Very, very brief introduction for channel knowledge map. And next, I move to, overview of existing channel knowledge map construction method. So you can think of a channel knowledge map construction problem, right? Is to recover the so-called mapping, right? Is a mapping from the arbitrary transmitter and receiver locations, their coordinates, in general 60, right? 3D for transmitter, 3D for receiver, to channel knowledge, or some abstraction of the channel knowledge, right? As I mentioned, right? Some statistical averaged channel knowledge. And but to obtain this mapping, right, usually we need to utilize two information. One is the historical channel measurement. That means that given this environment, right, some locations, right, we have already obtained some the channel management, but of course not all the locations, right? Otherwise, we do not need to recover the mapping M, right? So that means that we have some channel management in some locations, right, in this area. While we may or may not, we also have the physical environment map available, right? This give us some site information, right? For example, the topologies of buildings in outdoor environment, and or maybe their material properties, right? Especially in terms of interaction with electromagnetic waves, right? So you can think about, these are the input informations, and based on this information, so we're going to recover the general mapping, right, from arbitrary transmitter receiver coordinates Q and to our desired channel knowledge Z. Okay, so you can think of this as a general construction problem for CKM. Well, if you look at our existing methods, so here is a very, I think it's very coarse, way of categorizing them. But I think they represent some of the most classical methods for CKM construction, right? And we have, for example, retracing, right? The interpolation based, image processing or generative AI based, or more recently, wireless redundancy field based. I think all of them has already been covered by the previous speakers in this course series, and also recently we have a vision article in IEEE wireless communications, and also compared, which also compares the different construction methods, what are their advantages and also the limitations, right, compared to each other. So here, maybe I would just give a quick overview for each of them, right, just to maybe reflect, what are the recent, advance in each of these methods. So first, of course, is a retracing, right? Retracing is the most commonly used method for CKM construction. And you can use the available commercial software, right? For example, Wireless Insight, right? As example, or you can use some open source ones, right? Like Siona, right? And actually, if you look at all of this retracing based software, and all of them, right, they require prohibitive computational complexity. That means that you should expect, right, sufficient long time, right? Especially you have a big area, right? If you want to compute the channel, right, between any arbitrary transmitter and receiver location, that will be very time consuming. And also their accuracy heavily depends on whether you have a complete environmental knowledge. What I mean environmental knowledge, not just the locations or size of the buildings. It also involves the electromagnetic parameters, right, of the materials, right? And such as you can have an accurate CKM construction. Otherwise, right, what you construct will be highly inaccurate, or maybe just statistically, okay, just statistically consistent with the channel distribution in the given environment, but not accurate for exact location. Okay, so that's actually the limitation for all of this available, currently available retracing based CKM construction. Well, another popular method is interpolation based, right? We have, for example, right, kernel based, kriging based. So basic idea is that we consider the channel knowledge map as as a 2D, right? It's a 2D continuous function, right? It can be you can treat it as a deterministic function, or you can treat it as a random field, right? With a continuous values. Right, and then we already have some measurement, right? The channel measurement at some of the locations, right? We call the reference positions, and then based on that, right, we're going to use different types of interpolation techniques to predict, right, the channel values for at the unmeasured positions. Okay, so this is a general problem setup for this method. But the problem with the interpolation based CKM construction is that usually they are able to only recover a stationary. You can think of stationary environment channel distributions, right? Well, if you have a lot of sharpness, other heterogeneous object, in the environment, usually the effectiveness is compromised, right? in such scenario, because that's fundamentally limited, because this approach assumes that, right, we have a 2D or 3D continuous function of the CKM. Well, another method, probably more recent, is image processing, or generative AI-based CKM construction. So basically, they treat the channel knowledge map as an image, right? So basically, is that let's say we already have some measured channel map for some environments, right? And so we will treat the the environment map and the transceiver locations, right, as input for a neural network, which you're going to learn, right? Just like we'll be learn, for the images, right? So such as you can directly generate, some desired channel knowledge or features for the high fidelity channel knowledge map. But this approach, of course, I mean, it's very heuristic, right? Because fundamentally, we cannot see, the channel knowledge map, which is basically interaction of electromagnetic wave propagation with the environment, is the same as the how the image are generated. But it works, right? I mean, in some there's many works that show that actually there's some relationship, right, or analogies between image and radio maps, and so it works. But there's also some limitations, right? For example, this approach typically requires massive amounts of labeled training data. Okay, and also to my knowledge, they're only limited to 2D channel knowledge map, right? It will be difficult to extend to 3D. Or even, if you think of arbitrary transmitter receiver location, that would be 6D channel knowledge map. I don't think this approach, can be easily applicable to those generalizations of channel knowledge map. Well, you can think of maybe most recently is I think for CKM construction is the approach based on the so-called wireless redundancy field, right? So basically, this is inspired by how the image is generated. You see how the light travels, right, in the given environment. It's have some certain analogy as the electromagnetic waves. All right, for example, right, they both get reflected, scattered, diffracted, right? So based on that, right, they try to simplify physical retracing, right? You can think about this as a digital way to implement the retracing, right? So basically, the idea is that they integrate the physical retracing into implicit. You can think implicit, like continuous neural field, right? So this is the original idea of this so-called NERV2, right? And but the problem for that is that it takes a tremendous amount of time for training and also the inference. I mean the prediction for because of this implicit volumetric sampling. So the complexity is huge. I mean, of course, this has been used for the image generation, right? This is how this original idea come from, right? From the redundancy field, right? But if directly applying this approach for radio map, it seemed to me that actually you didn't really explore the structure of the radio map and also the environment. So I think in terms of computational complexity, there will be a serious issue, right? To simplify NERV2, right? This I think the more recent one is the so-called the Gaussian I think this paper is using a 3D Gaussian splattering, right? So this is the idea is that instead of using so many neurons, right, and they use a smaller number of the Gaussian splatters, all right, and that basically is some parameters you need to estimate, right, to fit the Gaussian functions, right? So this will help reduce substantially, all right, the complexity of NERV2. But it's still, right, they need dense, measurement points, right, such as you can get accurate Gaussian fitting, right, for the 3D Gaussian splattering, right? So I think, but you can see, right, I think if you look at this wireless redundancy field, right, WRIF based approach, you can see, right, they actually explored, right, this fact that actually for radio map or channel knowledge map, right, the scatterer induced EM interaction with the environment actually plays a dominant, a major role. Okay, so if you look at the idea, the common principle behind this approach, right, you can see that actually they realize that the scatterer actually plays this concept plays a significant role. So actually, independently, my group we also come out with a similar idea, but of course later you can see, right, the exact implementation will be different, but it's also based on the scatterer. Okay, CKM modeling and the construction. That will be the focus, of this talk and what I'm going to elaborate next. Okay, so what is a scatterer-based CKM modeling and construction, right? Actually, the concept is very simple, right? So basically, is that if let's say we divide the area into many smaller size grid, or of course, the size of grid is arbitrary, right? And then we look at the channel, distribution, right, within each grid, right? Then you will realize, right, in general, right, this channel will be just a superposition of a multiple paths, right, which is entering into this grid. Okay, well, if you look at this path, right, where they come from, right? Of course, you will see, okay, there's some maybe come from directly from the base station, right? If you have a line of sign, link from the base station, but in reality, usually they are from some dominant scatterers in the environment, right? Of course, here I say dominant is because we cannot really count any arbitrary size physical scatterers. Otherwise, you will have infinite, right? This kind of so here you can see, right, when we see n here is represent the number of scatterers, we want to select the dominant one, right? So this is very typical. We all know, right, the multi-pass channel model, right? And then each of the paths, right, you will have a gain, right, and a phase, right, and also this delta parameter is in front is represent whether this is a line of sign or a non-line of sign link, right, from the scatterer. Okay, so this is, I think, everybody can imagine, right? This is very intuitive and also consistent with what the propagation that takes place in any practical environment, right? But the thing is that how to make use of this, right? For this concept, I mean, these multipaths are due to physical scatter. How to make use of this concept, to do more efficient channel modeling and the channel map reconstruction, right? That is relatively less exploited, right, in the previous in the existing literature. Okay, so maybe one thing, right? For example, right, if we only interested in the channel gain, right, within each grid, right? So actually you can show that, right? This is because in this each small grid you may have some local small scatterers, right? So that will cause small scale fading, right? So their channel will change even within, right, the each grid, right? Even it's a very small grid, right? So if you really want to characterize the small scale fading, right, for the channel within each grid, right, I think is a formidable task, right? It's not possible, right? So you can think about, right, if you think about average channel power within this limited size grid, right, then we can prove, right, actually the proof is given in this paper, that you can think of it, this is it's just equal to the summation, right, of the dominant paths, right, from this scatterers, right, entering into this grid, right, and their average power. Okay, and also we can only consider, right, those paths that has a line of sign, right, clear line of sign pass, right, from the scatterer to the receiver grid. Okay, so you can think of where we can get this information, right? Whether each scatterer has a line of sign with the particular grid or not, right? This is actually need to be provided by some prior available environment map, right? And then the beta NK, right, represent actually is a scatterer, to the receiver, each scatterer, right? Scatterer N to the receiver, a grid K, right? The line of sight path, right? If let's say this exists a line of sight path, right? And then the power gain, right? And this one we need to model it, right? We need to model it. How much power this particular grid, let's say grid K, right, get from the scatterer N, right? Well, you see, this the good thing about this approach is that I do not care about how the signal propagate from the base station to the environment, because to each scatterer, maybe there's reflect by other reflectors, right? So it's very complicated multi-hop, right? So that's it's very difficult, right? So the good thing about this is that we just select the dominant scatterers, right? Which we'll think of the last reflection, right, from the last mile, right, reflection from the scatterer into the grid, right? If there's a line of sight link available, right? So this I think capture the physical EM propagation in the practical environment, and also avoid modeling the details of the actual multipath, the complicated multipath cascaded channel modeling in the retracing, for example, in the retracing wireless redundancy field, right? If you're familiar with those approach, right? Simplify, right, their modeling, okay, complexity. So with this in mind, now we want to focus on the channel gain map, right? So channel gain map, what I mean is that we're just interested in the power, the average power in each grid, right? We just want to recover, the power, the channel gain distribution in this area, and okay, so in this case, of course, I mean later I will also talk about this approach. The scatterer-based approach is very general. Actually, you can use it to reconstruct any other type of channel knowledge map. But in this work, we start with the channel gain map. So in this talk, we'll also focus on the channel gain map, right? So based on the previous formulation, right, you can see, right, for any grid K, right, you can model the channel power, the average channel power, as a summation, okay, of n, right? I mean n is represent the number of scatterers, right? And well, delta is represent, whether there's a line of sight, right? It's an indicator function, right? Take value 0, 1, whether there's a line of sight from the scatterer to a particular receiver grid K. Well, beta nk is we need some modeling, right? The beta nk is the how much power, right? How much power is from a particular scatterer to the receiver grid, right? So it will depends on the position of the scatterer and also the receiver grid, right? So we calculate the distance. We follow, in general, you have a distance dependent power loss, right? So alpha, you can see the equivalent path loss exponent, right? And the S and R is the location of the scatterer and also the receiver grid K. You can take the center position of the grid K, right? Well, beta 0, you can think of as a reference path loss for this environment. So out of this alpha, beta 0, later we can estimate it. But maybe most importantly is the parameter is this gamma nk, right? So this gamma nk actually is a called a scatterer response coefficients, right? So here I have a graph to illustrate it, right? So when this scatterer, when the signal from the base station, right? I don't know how they propagate it, right? Eventually will come to a building, right? And this building, a very complicated electromagnetic interaction, right? I don't want to bother to model the detail, but I just treat this scatterer as a new transmitter. It's as if it's a new radiator, right? And then you can think about, right? It's as if, right, this scatterer redistribute the power from the base station, right? No matter how complicated process it has gone through, right, to reach the scatterer, but it will just redistribute the power in the spatial, right, dimension, and then we just characterize, the different, we quantize the continuous space angles into some solid discretized, volume, right? And then we just assume, right, a given angle, this discrete angle range, we have a particular gamma nk, right? This response coefficient, right? So you can think of this response coefficient is a way the scatterer redistribute the power from the base station into different directions. Okay, one, of course, the receiver grid, right, will have a particular direction with this scatterer, right? So that will take the value of that particular gamma nk, right? So you can see, right, this is very simple modeling, right? It's a very simple, it's just based on the, the two, I think, basic concept. One is that we just care about the last mile, the last hop, right, from the scatterer to the receiver grid. And second one is just take, consider the scatterer is as equivalent, a new radiator, right? So we have this very simplified formulation. Now the remaining task is that how to estimate this parameter, right? In this scatterer-based channel gain model. Okay, so so as I said, right, so the remaining task is to estimate, right, the scatterer parameters, right? What I mean is the angle dependent scatterer response coefficient, and also some common parameters like alpha and beta 0, right? But they are very limited number, right? So if you consider you have a region, right, you have arbitrarily large, right? Of course, I mean, if you can divide it into many grids, right? If you assume each grid size is fixed, right? But the number of parameters, right, in this modeling, right, it just depends on the number of dominant scatterers, right? And of course, and how you quantize, right? How many angles, right? You discretize, right? In the continuous space, right? But all of these are controllable, right? So you can see that we only have a limited or sparse, very sparse, scatterer parameters, right, to estimate, and this is controllable, right? But this is very different from the the EM, traditional like EM-based retracing, or WRF, right? The radiance field-based one, right, which is require massive parameters, right? Even you use a 3D Gaussian spattering, right? So you can think, right, that this is this model is completely controllable, right? So what we need to do is that it's just to we given some of the channel gain measurement, right, in the given area, some grids, and then use this scatterer-based model, and then we're going to recover the scatterer parameters, and then based on this very simple model, right, we can construct the channel gain map for any other unmeasured grid locations, right? So it's very simple approach. So the problem, right, the scatterer parameter estimation problem, right, can be formulated as the optimization problem, right? You trying to minimize the estimation error of the channel powers, at measured grids, right? Because at some grids you already have the measured power, right? And then you use because you have the parameters, right? You have the scatterer parameters, for example, the number, the positions, and the response coefficients, right? We collect them in this omega, right? It's a set, right? And then we just, if your parameter estimate are accurate, right? I mean, based on this previous equation, then you can pretty much predict the power, right? At those grid you have already measured, right? The average power, right? Okay, so that means that their error should be small, right? You can think of mean square error, right? So here we consider a very general formulation. So we have a loss function u, right, which is a decreasing function of the estimation error, because sometimes if you just take absolute mean square error may not be good. Later I will explain, right? Sometimes maybe we take a normalized or some other object loss function, but in general you can think about, right? We want to minimize, we can minimize the errors, right, between the predicted channel power with the actual power you measured, right, at this certain number of locations, right? And we want to find the parameters, right, that best fit, right, the model. That means to minimize the errors. Okay, so now there are three key issues, right, in this in how to solve this problem. You think we should take good consideration. The first one is that the scatterer parameters, right, for this map construction. So what are the parameters are essential or more important in omega, right? As I said, right, you can think about it, right, is the scatterer number, right? How many of them, right? What are their positions, right? Or or maybe some other parameters. So whether what is the size? Is the size relevant? Okay, or maybe the response, the response coefficients, right? Previously, we just model as a, angle dependent, right, scatter response. But in practice, right, there could be many others, or maybe other more efficient representations, right, for the scatter parameter. So we need to consider, right, what are the most efficient set of scatter parameter, because their number will determine the complexity, right, of solving this problem, right? It's also the complexity of our channel knowledge map model. Okay, because I said the good approach about this method is that we have a controlled, degrees of freedom, right, in terms of the number of scatter parameters. Okay, the second one is that shall we consider the scatterers they are physical scatterers, or maybe they are virtual scatterers, right? So the good thing about physical scatterers is that they match the real geometry, right? So if you see, oh, there's a big building there in your environment map, you put a physical scatterer there, right? But the question is that, if you have too many, objects in the environment, and for each of them, right, you consider as a physical scatterer, then the complexity, right, the number of scatter parameters will also scale up. Okay, but if we consider virtual scatterers, I mean, later I will elaborate more on the definition for virtual scatterer. But you can think about those are more flexible, right? Maybe based on the physical scatterers, or maybe totally it just virtually existent, right? So that means that with some scenarios, right, we can put a virtual scatterer there to represent many physical scatterers, right, in the neighborhood, right? As if as long as they have similar effects, right, to the model, right? So you can think about virtual scatterer will be more flexible, right? They will give us more degrees of freedom, right, to control, right, the complexity, right, the parameter selection and estimation. And later I'm going to show you actually virtual scatterer in some scenarios performs better than the physical scatterer. Well, the third issue is that usually ignored in the existing literature is that the channel measurement locations. That means that because I want the model, right, to fit the power at certain locations, right? But you measure the power, right? But are the locations arbitrarily good? Okay, or you can think of more fundamentally, right? This is something like a spatial sampling problem to me, right? That means given a field, right, given an area, where we should sample, right, the location, right, where we measure the power, and it will help us better, I mean, given the same amount of training, right, the measured data, which will give us a better reconstruction performance for this field, right? So if you think deeply, right, the measurement locations, right, for the power or the channel, greatly impact, right, the CGM construction accuracy. So later I'm also going to show you for this scatterer-based approach, right? So you can think, right, all of these are key issues, right? We need to take into consideration if we want to have a very good reconstruction performance for this approach. Okay, so now let's first consider the physical. Sorry, there's a call coming in. Let's first consider the physical scatterer-based approach. Okay, and then I will consider virtual scatterer. So for physical scatterer, as I said, right, you already know the location, right? You already know the location of the scatterer, right? And assume we have the environment map, so we already have the line of sight availability, right? This indicator function already, right? And then the locations are known, right? So what I really need to estimate is just some common path laws and exponent coefficients, alpha, beta 0, and the angle dependent the scatterer response function, right, per sector. But how many of them, right? It depends on how many discretized or quantized sectors, right? M, right? For example, what is shown here is just 4 sector, right? I mean, M equal to 4. Of course, if you want to get better resolution for each scatterer, you can increase the M. Of course, that would be also means you have more parameter to estimate, right? So for physical scatterer, you can see, right? The parameter set you're going to estimate are not really that many, right? As I said here, right? If you put all the scatterer response coefficients into a vectors, right? That will be a vector V, and then you have alpha, beta 0. There's 2 scalars, right? But actually, if you're using the loss function as a mean square error, right? Let's say we take a mean square error as for the loss function. Then you actually this estimation problem, right, is a minimization problem. It's not really easy to solve because all of these parameters, they're non-linearly, non-convexly coupled, right, in this objective function, right? So if you want to globally solve, what is the optimal v and alpha beta 0, right, for this minimization problem, is very difficult, right? So what we propose is to use the iterative estimation of this parameter by using alternating optimization, right? So the idea is that let's first fix the v, right, and the beta 0, and then you estimate alpha, right, and then you fix the other two, you estimate beta 0 and then v, right, and each time you estimate one and with the other variables being fixed, and then you do this iterative until there's no further improvement in your loss function, right? And so this is doable, but whether this is the most efficient approach, I don't know. I believe, right, there'll be should be more efficient approach to solve this problem, but this is what we presented in this our initial work. Okay. And maybe one thing I just want to comment is that because this also when we submit the paper, some reviewer asked is that how to obtain the average power in each grid, right? Because each grid has some finite size, right? If you look at the traditional channel knowledge map, usually they consider the channel, right, at any particular location, right? As I said, right, if you think with each grid, you have a small scale fading, right? It's not feasible, right? So when we consider channel GIMP map, actually we consider average power within the grid. But in the practice, right, when we see, right, we have a average power measured in this particular grid, right? But how to practically get this average power, right? So we think about this comment. I think we can do two ways. One is that you send a robot, okay, that move randomly in this grid, and then you collect the small scale channel fading power over a certain time, and then you take the average, right? That will be the average, the power, okay, for representing this grid. Or you may you want to do more efficiently. No, you may another way is that you use a multi-antenna, right, receiver, which you can resolve the multi-pass signal power, right, from different directions. And then you can add them up, right? And this will also help you to get an average power in this grid, right? So you can think in practically when we obtain the channel power measurement, we can take different means, but you have to be really the power averaged over all the spatial angles, locations, or even frequencies, within this given grid, right? So that will take as the average power. And this is also useful, right, in a lot of network planning problem, resource allocation problem. What we need to know is actually the average power within this grid rather than exact location, right, the instantaneous channel. Okay, so the next one I want to comment is that the measurement location selection, right? Just now I mentioned, right, the spatially sampling problem. Actually, mathematically, all right, you can show that, all right. This, when you want to solve the scatterer response, right, the V vector, actually is highly depends on the matrix F, right, multiplied in front. Well, the matrix F actually, is if you look at the entries, right, it's actually indicate, right, if you have a line of sight, right, I mean link from the scatterer to the grid, okay. So if that direction, right, if you have a line of sight link, right, then the entry is given by this, right, this particular value, okay. Well, here assume a beta 0 alpha is already fixed, right. I say this what I mean is one iteration, right, for estimating the V, right, the scattering response vector. Right, but you can see, right, this is what, right, this is actually a least square, okay, estimation problem. We know, right, least square problem, right, the performance highly depends on the matrix, the structure of F, right. So here, due to a time constraint, I won't elaborate on that, but actually what I mean is that by analyzing F, actually we can get some desired properties, right, for the location, right, the desired measurement location, right, such least square problem or solved, right, to estimate the V, right? For example, here to shows that actually what we get is that, okay, if possible, right, if you can choose the grid, right, to measure the power, you should consider this grid, right, as close as to the scatterer, the physical scatterer, as much as possible, okay? and also try to make sure these scatterers, this measurement grid, right, which appears in all possible directions, right, of this each of the scatterer. That means if you have an unmeasured grid, right, in this direction, right, then you should put your grid, in this, you should put a measurement grid, right, also in this direction. Otherwise, you will have a missing data. You will have a missing data that would result in some poor structure for F, which is a least square problem estimation, not efficient. Okay, so this is, you can see also, right, for this physical scatterer based approach, right, if you really want to get a good reconstruction of the through this scatterer parameter estimation, you have to ensure, right, the measurement grid location, they're good enough, right, such as you have a good structure for the F matrix, right, then you can recover these parameters. Right. So this is actually later you're going to see this is a drawback of physical scatter based model, right? So because that means that you have to have the channel measurement at some designated locations. Otherwise, this approach will not work satisfactorily. Okay, so this is I think this I already introduced the physical scatterer based modeling and the channel gain map reconstruction. But actually there's some challenges for this approach, right? One is I already said, right? The solvability of the problem, right, depends on designated measurement location, right? That means that if you put the measurement location not properly, right, you may have a yield conditioned least square problem, right, which is result to very poor estimation, channel gain map estimation performance. Okay, but while on the other hand, right, you can think about this. Also, another issue is that if you have a dense physical scatterer environment, right, then you will have many scatterers, right, as I said, right. And then the parameters, right, for the scatterer will scales up rapidly, right, with the physical scatterer density, right, which is leading to uncontrollable and also prohibited modeling and estimation complexity, right. So this is a motivate us to build a virtual scatterer model, right, with a controllable complexity and the model's scalability, right. And this, I think, is more promising, right. So that means that regardless the size of the map, the area, or the actual the physical scatterer, we can always select the outside the most appropriate size for the virtual scatterer numbers and also their parameters, right. So this is the motivation for the virtual scatterer model. So what is a virtual scatterer model? You can think about, right, they are tunable. They have a tunable number of them, and also their scatterer positions, right. So you can think about two illustrative examples. For example, right, in one case, right, you may have a very large scatterer, right, which has a very heterogeneous interaction with the electromagnetic wave, right, from the base station, right, from the transmitter, right. So in this case, right, we can split. Right, we can split the one physical scatterer into multiple virtual scatterer, right, to get better representation, right, of a scattering function. Well, on the other hand, so maybe we have a very small, closely located physical scatterers, but with a very similar propagation characteristics, right? Then we can merge them, right? We can merge them into one single virtual scatterer, right? So you can think, right, based on the physical scatterer map. Okay, of course, I mean, this assume you have that available information. Then we can do a merging operation or splitting operation, right, to control, right, the number of virtual scatterer. Of course, this also works even you do not have a prior environmental knowledge, right? I mean, you don't have an environment map. Then we can also, randomly assign some virtual scatterer number and the position, and then successively refine it. So you can see, right, this is a good flexible. The good thing about this model, virtual scatter model, is that you have a flexibility, right, to control the number and the positions. And not only that, if we look at the virtual scatterer model, right, there's a very important one is the scatterer function, right. Now previously we divided the angle range, right, into m sectors, right. We assume each sector has a particular scatterer coefficient, right? But I also mentioned the limitation of that, right? If in that direction you do not have a measurement grid, right, then you have a data missing, right? Your matrix M, F, the corresponding attribute or rows is missing, right? They will lead very inefficient parameter estimation. But here, since this is a virtual scatter, right, it doesn't represent the physical scatter, right? But we know, right, in practice, right, the angular scatter response, they are correlated, right? Usually that means adjacent, right? If the angle they are close to each other, usually they are correlated, right? So this is motivating us to think about, right? Maybe we can model this, the cross sector, right? Cross sector scatter response coefficients, right? As some, based on some statistical model, right? So for this work, I mean, another recent work we submitted, we're using the Gaussian, right? The Gaussian function, right? To model this correlation, right? So that means that even we have random measurement location, I mean, in any given direction, we don't really have a measurement data, right? Measurement grid, but we can still use the correlation function, right, to predict, right, the coefficient, all right, in that particular direction, right? So this helps us solve the problem that the missing, the angular direction data, right, in the previous physical scatter-based model. Okay. So, but of course, this also means that the set of parameters, right, in the omega will be now more abundant, right, compared to previously physical, right? Because now in terms of number, position, scattering function, right, they are all in the set of omega. But of course, I mean, their numbers are controllable, right? It's not necessarily equal to the number of physical scatterers, right? So in reality, actually, the sample size you can control it, based on the amount of measurement data available. Okay. So now the problem, I modified the previous estimation problem now for the virtual scatterer. They are very similar. All right. The only difference now is that the parameter set, all right, the omega now has a more components, right? The scatter number, positions, response functions, right? They all included, right? Of course, I mean, when we assign the virtual scatterer, we also have a confined region, right? Because otherwise we may have some overfitting problem. So we constrain them in a particular set, right? And other than that, right, it is very similar to the previous physical scatterer. But now is that the estimation, the problem, the optimization problem becomes more involved because now you have the positions, right? The position is also now the variable, but it is very highly nonlinearly non-convexly coupled with the other variables, right? So how to solve this problem? And what we propose is that we propose a progressive estimation with steadily increasing the scatter number, N, right? So the basic idea is that we start with a small number of virtual scatterers, okay, and trying to estimate those parameters, and then we progressively add increase the number of virtual scatterer and see whether you can improve, the overall loss function, right? If we can improve, then we increase, right, the number of virtual scatterer. If not, then we stop. Okay. So with this progressive estimation, right, we can also have, we can automatically set, reach to the optimal scatter number. Another one is that in the each iteration, we also do an inference problem. I mean, for the cross-sector coefficients, right? If let's say we have some missing direction, we are going to use a Gaussian regression to recover that, right? By using the inference, standard inference. So this will remove the constraint on the channel measurement locations, right? So later we're going to see the performance will be more robust. Okay, so now next I will show you the performance evaluation. Okay, so basically, we consider two scenarios. One is the sparse scatterers, right? We only have 7 scatterers. You can think of this all dot environment, right? And we consider 2 types of measurement locations. One is a type 1, right? The measurement grids are selected around the physical scatterers. Okay, so this is what we showed, right? Previously, theoretically, this is desired. Well, type 2 is randomly, right? The measurement grids are randomly in the region. Right? Let's see, how their performance are different. Okay, so you can see, right? This is this is just the ground truth map is generated by using ray tracing software. We haven't done the real field test yet, right? So this is simulated, right? Assume this is a true map. Okay, the ground truth, and then we use the physical scattering model and we show the estimation results. And for these two type of the measurement grid distributions, as you can see, right? If you deploy the measurement grid right close to the scatterers, as a theoretically predicted, right? You have a mean square error, right, which is much lower than the other randomly distributed measurement grid locations, right? So this shows also the physical scatterer modeling based approach highly depends on how you assign or the locations for the measurement, power measurement. Okay, well, the second one, the second simulation result is to compare with other conventional method, right? For example, expectation maximization or kriging is a kind of interpolation based method. But you can see, right, if you choose the type, I think that this type 1, right? I mean the measurement grid location near the scatterers, we can achieve much better performance than the benchmark, right? Actually, you can see the mean square error reduced substantially. Of course, this depends on the fact that you have to make sure your grid locations are selected properly, right, near the scatterers. Okay, and this shows some performance in terms of number of measurement. Of course, the more measurement you have, okay, you have more data available, right? So the mean square error drops. So for the methods we compared here, the consistently, right, the physical scatterer based model with the type 1 measurement location, I mean the near the scatterers, will perform the best, right, with the lowest mean square error. Well, the second simulation is for the dense scatterer environment, right? So in this case, in this area, we have 30 physical scatterers, right, of different sizes, dimensions. And here, actually, instead of using mean square error, we're using normalized mean square not loss function. The reason is because we want to enhance the recovery of fine details, especially those low channel power gain weak signal subregions, right? Because we think, for channel gain, it depends on how you use the channel gain map, but usually we use it to improve the coverage, right? So that means that the weak signal coverage, right, the grids actually is it may be more important than already you have a strong coverage, right? So this is why I want to put more emphasis on the the fine details or the low channel gain the subregion, the grids recovery, the channel gain recovery. Okay, so in this case, right, we compare the physical scatterer, right, and the virtual scatterer, okay, and also kriging, right? So you can see here the virtual scatterer can give you a normalized mean square, a substantially reduction, right, from 6.1 to 0.42, right? Even using the the measurement grid location in favor of this physical scatterer model, I mean near the scatterers, right? So this shows that actually the virtual scatterer approach is more efficient, right? It's more effective, right? Especially you can see, right, in terms of recover the sharp boundaries and the low power gain subregions, right? It's done much better job than the physical scatterer. Okay. And we also, for the virtual scatterer, we also try the two types of, the measurement grid distribution. I find that actually actually they're not much difference, right? Sometimes a randomly selected even performs better, slightly better than the measurement location near the scatterer, right? The actual scatterer. So this means that the virtual scatterer based method is more robust to the channel measurement locations selected, and this is desirable. And this results also shows, right, consistently, right, the virtual scatterer performs better when the number of measurements, right, the grids increases. And also estimating, you can see, right, in our reconstruction, the model, right, the estimate number of virtual scatterers automatically increase when you have more measurement data available, right? Because you have more data available, right, your model size can grow, right? So, in our progressive algorithm, right, we gradually increasing, we can gradually increasing the number of scatterers in the model, right? So this shows that the flexibility of the virtual scatterer model, right? You can, based on the amount of measurement data, you can always select the best, scatterer number, right? Such as you get the best estimation results. Okay, so I think okay, so this is already quite long discussion already. So now let me quickly conclude my talk. So basically, I introduced a scatterer-based channel modeling approach. I think is a quite interesting, right? It's also promising to provide a lightweight, now also physics-inspired mapping, right, from physical environment to channel knowledge. And we propose efficient channel map reconstruction framework, right, by exploiting the environmental structures and also the inherent spatial channel correlations based on this very simple scatterer model. And we propose two scatterer-centric channel game map modeling estimation method. One is based on physical scatterer, the other one is a virtual scatterer. So I think the physical scatterer, the main limitation is that depends on the designated location for the channel measurement. And also, it's more suitable for the outdoor environment when you have a sparse dominant scatterers. While the virtual scatterer overcome the issues of physical scatterer, and even with a random location channel measurement, it works very well. And also, it's suitable for the indoor environment where you have dense, uniform scatterers, and it also can guarantee the performance. Now, in terms of future directions, I think there are many, right? If you think about this dual concept, right? This scatterer-based models. I think not just channel game map, but you can apply it to develop other types of map, right? Like power map, spectral map, angle map, and so on and so forth. And so far, we only done the simulation-based, right? Based on retracing validation, but it will be good to have some field tests to evaluate the actual performance of this approach. And also, think about time varying environment. Now, how to, update the channel map, right? Based on the scatterer model. It's also interesting because I think, model the scatter, change will be relatively easier than, reconstruct the whole channel map. Okay, if you're using some other approaches, existing approaches, right? So I think scatterer modeling has also advantage to enable very efficient channel map update based on the some dynamic update of the scatterers parameters. Okay, and also how about the cross environment transfer and generalization of scatterer model? I think transfer radial map or channel map transfer learning is a very challenging problem. Actually, what I mean is that if you have learned, right, some channel map and also for some environment, now how to transfer or how to embed the useful knowledge, right, you learn to some unknown environment, right? I think this is still an open problem. I think scatterer model provides, probably, a new approach where we can think about, how to do this transfer, right? Okay, transfer learning. I think there could be something promising along this direction as well. And also, as I said, right, we propose some algorithms, right, for the scatterer parameter modeling and estimation, but in no way they are the optimal ones, right? I think in terms of modeling efficiency, in terms of algorithm efficiency, there are still much room to improve. And also, I mean, you think about CKM applications, right? So here, what I mean is that, try to explore the virtual, physical scatterer, right? Think about the channel map, right? What kind of map, right? Game map or angle map, whatever. Think of now there are functions of the scatterers. Okay, think about this, right? And this I think will help us to solve some application problem for CKM, right? For example, sensing localization. Okay, or some RS deployment problem. It will give us some new approaches, right? That can help us solve those problems, those traditional problems, right? For more efficiently, because now we have a new representation, right? Which is, has a very controllable, parameter size, right? Related to the scatterers, right? So this will give us a new, I think, a new direction, right? We can explore, this the CKM application design problem. Okay, so with that, I think it's the time for me to stop here, and I will look forward to addressing your questions, if any. Yeah, thank you.
Thank you, Professor Zhang, who gave us in-depth overview of CKM a detailed elaboration on scatter-based approaches and also share with us some future directions. We have received some questions from the online audience. The first question is related to risk as follows. The question, the equation Z equals to M of Q establish a spatial mapping. However, if the physical environment undergoes dynamic changes, for example, large moving vehicles, does this static function M fail? In 6G networks, do we need to introduce a time dimension to, for example, upgrade it to a time varying function or achieve low cost update through incremental learning?
Okay, I think that's a very good question. I think this is also common concern for the channel knowledge map. So this is, I think one of the slides I already briefly discussed that, right? So usually, what we do is that, we offline, right? We first offline construct the channel knowledge map, right? Based on the environment map and the historical channel management. Of course, I mean, this will be accurately characterize the environment which you have static dominant objects, right? Scatterers, okay, for example, right? But we also know, right, the environment may change, right? The building location, maybe some building may be gone, right? We have to, over time we have to monitor, okay, and update, right? So this is the real-time update phase. But I think the key is depends on whether you need to do frequent update or in how fast or how slow you need to do the update. It completely depends on your application, right? If, for example, I want to do some network resource allocation, right, in the small time scale, right, then of course you need more frequent, right? You need to really have that time dimension, right, to frequently update your channel knowledge map, right? But let's say I want to do some, okay, like a base station deployment, right, like a RS or deployment, right? Then there's mainly not really based on the small scale, change. It mainly depends on the, the environment, right? The topologies of the static scatterers. So for those cases, right, maybe you do not need to frequently update the channel knowledge map, right? So as I said, right, of course, I mean the in general, right, you do need the CKM update, but how fast it is required, it depends on how you utilize the channel knowledge.
Yeah, thank you, Professor Zhang. The second question, the introduction of virtual scatterers to provide greater flexibility is highly inspiring. However, if virtual scatterers undergo flexible merging and splitting, do they somewhat degrade into pure mathematical fitting tools, losing their correspondence with the actual physical environment? In complex real-world non-life science scenarios, how do we guarantee the extrapolation and generalization capabilities of this virtual model in unmeasured areas, given the sacrifice of some physical interpretability?
Yeah, that's also I think is a very good question. I think I have one slide. Okay, first of all, okay, the example I give you, right, it's just for the illustration. What I mean is that for the given environment, because our objective is to try to recover the channel gain, every channel power in each grid, right, with certain resolution. So my point here is that you do not really need the number of scatterers in the model, which is exactly correspond to the physical scatterers, because anyway, right, it depends on how much contribution, how much effects these physical scatterers, right, make to your overall model prediction, right? So what I mean is, it doesn't mean that our algorithm is necessary that every time you have to fine tune, whether this physical scatter you need to split into one or two, or whether you should merge some. No, I'm not meaning that. I'm just saying that you can if you do that, right, maybe you can have a similar representation, all right, of the physical propagation, right, but with less number of virtual scatterers, or more efficient, given the same number of virtual scatterers, but we let them more accurately represent the physical reality. Okay, So, but in the algorithm, the actual algorithm, as I said, right, you just progressively increase the number of scatterer, right? And then you optimize their positions, right? So this is done by the algorithm. It doesn't mean that in the algorithm, we have to really do this manual tuning for the splitting or merging, okay? But now I agree with you, right? Any model has certain, accuracy limit, right? So what I show you here is that if you have, I think one of the simulation result I show you is that if you have more data, channel data measurement in the channel gain map, that means you have more grids, you measure the average power. The algorithm itself will automatically increase the number of virtual scatterers, right? Because you have more data to help you recover the parameters, right? And then it will lead to more accurate, channel gain map reconstruction, right? So what I'm saying is that, this approach will allow us, to flexibly control, okay, the number of virtual scatterers, right? And to best fit your data. Okay, so if you think fundamentally, right, this is just, I'm not saying that, let's say, you only have 3 virtual scatter that can always get the accurate performance. No, right? It always depends on, how many training data you have, right? If you have more training data, then you can increase the number of virtual scatter, and then you automatically get better performance. Okay, I hope I addressed your question. Yeah.
Right. We have a follow-up question here. The performance results are highly encouraging. Regarding the mechanism where the number of virtual scatters automatically increases with more data, this resembles adaptive model complexity in machine learning. How does the system decide when to stop adding virtual scatterers? Is there a penalty mechanism similar to cross-validation to prevent overfitting when measurement data is extremely dense, ensuring the model maintains strong generalization in unmeasured areas?
Yeah, so that's very good comments. Yes, that's related to some fine details about how we implement the algorithm. If I recall correctly, in that paper, when we implement this algorithm, actually we didn't really go into the, many details because this is very initial work. I think you can refer to this paper. I hope it's available on arXiv. So basically, what we did now, if I recall correctly, is that we just, we increase the number, okay, the virtual scatter until, and then we estimate the parameters, right? We estimate the parameters until I think I have the optimization problem until we cannot further improve, minimize the objective function. Okay. So you can think of if you have more training data, I mean more grids with power management, this iteration will go in with more numbers, right? Eventually will stop, let's say maybe N3 equal to 6, it will stop because with N3 equal to 6, right? After you estimate all the other parameters, you cannot see you have an improvement, further improvement for the objective function. Then algorithmically will just stop, okay? But you just now you also raised a very good point as about given this data, right? This data, whether we should use all of them for this estimation or we should split them into some training and validation. Those, I think in this paper we didn't do that, but it's a good point. I mean, it depends on how you use the training data, and this is very similar to in machine learning, right? This is some similar concept. So I think all of these details, I mean, we can investigate in the future work and see how to improve, this estimation result. Yeah.
Thank you, Professor Zhang. We have 3 more quick questions. In practical 6G action network deployments, we must also consider real-time computing constraints. As channel measurement data is continuously fed and the number of virtual scatterers automatically climbs, does this cause the computational complexity of the parameter estimation optimization to increase exponentially?
Okay, so I can address that. This is what I'm saying, right? If you look at existing method, right? Now let's say all the existing method, right? If let's say, I think I have a table there. Let's say I want to do CKM update. Okay, I would say, right, when the new data comes, right, how to update. I would think they will be more complicated than the virtual scatter-based model. Because for virtual scatter model, actually, I just need to find the virtual scatter that correspond to the change in the physical environment to do the update. Although we haven't done that, but intuitively, I think, right, that can be much more efficient, right, than the existing method for the CKM update, right? This is just, I said, this is just my personal intuition into this, right? But if you think about, right, for example, image processing, right? If you have some change, right, in the part of the image, right, what are you going to do? You have to retrain the whole neural network, right? But for virtual scatter model, you can just, locate, right, what the scatterer, right? You need to update, right? The remaining scatterer, you don't need to change it, right? So conceptually or intuitively, I think virtual scatterer, if you want to do CKM update, virtual scatterer, at least it can provide you a more efficient way to do it. Yeah.
Yeah, the last two questions are related to measurement samples. Is there a more general way to evaluate how important each measurement sampling point is?
Yeah, that's a very good question. I think you are asking some fundamental question because what we did so far is just a heuristic observation, based on simulation of some simple analysis based on the least square problem, right? The structure of the F matrix, right? If you remember, right? But of course, in general, right? I think there's a deep theory there. Right? I mean, how you can select, given a field, right? Distribution, how you're going to select the sample, right? Location, such as based on these samples, that you can reconstruct the model and predict the other unmeasured location, channel with a better accuracy, right? If you really think about it, it's not a trivial problem. Now, how mathematically you can formulate such problem? This is an all open problem. As I said, we just started with this approach. I mean, there's a lot of open questions, right? Challenging questions that remain to be addressed. Yeah.
All right, the last question. It seems that the selection of measurement sampling points is limited by matrices used in estimation. But if an estimation method is matrix-free, would those sampling points no longer have constraints like condition number and linear dependence?
Yes, I said, this is actually, I said, if you recall, right, this is, I said, the drawback for the physical scatter approach, right? So basically it means that, for example, right, I think I have a graph to illustrate that, right? If you where is it? I cannot remember. Oh yeah, this one, right? So you can see, right? For example, if this direction, right, from the scatterer, right? This direction, right? I want to find the response coefficient, right? But I do not put any scatterer in this direction. Then the missing, right? The information will be missing, right? Then you cannot get a good reconstruction, right? For any unmeasured grid in this direction, okay? But virtual scatterer somehow overcome the problem, right? Based on our initial result is that, because you have this correlation, right? Over adjacent angles, you can correlation. So maybe you don't have direct measurement in this direction, but you have, maybe it's this direction or that direction, and then you use the correlation, the Gaussian function, right? It's like a self-recovery, right? For this coefficient, right? Usually it works quite well. So this is, based on the simulation result, is overcome the problem for the physical scatterer, right? Which is you have missing data or missing data in certain direction, angle, direction, right? That is somehow overcome based on the simulation, what we observe, right? Overcome that problem. But fundamentally, right? How theoretically, how mathematically to prove that? I think we haven't got better result yet. Right? It still need further investigation. Yeah.
Yeah, there's still a lot to address. All right, thank you very much, Professor Zhang. In the interest of time, we cannot go over all the questions, but feel free to email your further questions to us. Here, I would like to thank the audience for taking your time to watch the live and the videos. This is the last lecture in the CKM mini course lecture series, but I do hope this is the beginning of your exciting journey to explore the CKM area. Finally, we are excited to announce that we'll hold the third CKM tutorial and organized the third CKM workshop in this year's IEEE ICCC at Wuhan, China, 7 to 9 August 2026. So if you are working in this field, welcome to submit the paper to the workshop. And if you are interested, also feel free to come and chat with us. With Professor Zhang's talk, let's conclude the CKM mini course series. Let's thank Professor Zhang again, and thank you everyone for your participation.
Yeah, thank you everyone. Thanks, Junting. Yeah.
Thank you.
Okay, bye-bye.
Bye-bye, see you.
Bye.